Okay then guys, let's have a quick look at this paper. It's the June 2009 C3 paper for WJEC. Let's have a look through the paper, see if there's any surprises then as we go through it. It's a 90-minute paper, of course, as usual. We've got a formula booklet and a calculator. We should have our own calculator there. All questions need to be answered. We need to just put down the method that we've used, and we need to show our workings. We've got the marks on the right hand side, and we need to present our work in an orderly manner. So here's Simpson's rule. The nice thing is with this one, the integrand's quite easy. Here, easy to put in the calculator and work out the values, and it's a simple Simpson's rule, so that's very straightforward, isn't it? If we work to 60p, then the final answer around to 40p, we should be okay with that approach. Counter example here, we try theta is 0, 90 or 60 for cos. Those would be the first three things to try. We only need one instance where this is not correct to show that it's false. So one of those values hopefully will give that this is not true. This is a trig equation. This is cosec here, so we need to replace the cot squared by its cosec squared equivalent, and we'll have a quadratic in cosec, which we can hopefully factorize and then work out what the sine value is and solve. So that's B, and that's a nice question again too, lovely. This is an implicit function. Dy dx is easy. Run along the row, differentiate term by term, treating the y's as functions of a function and using that rule. Here we've got a function of t, dx dt, dy dt, which we need to get dy dt and then we get dy dx. When we get dx dt, and then we simplify our answer as much as we can. So again, this looks fairly user-friendly, nice question to do. So no surprises so far in this paper. Number 4. Here's a function of x, stationary value, so that's differentiation. Here's the actual answer. So we verify this equation is what we want for a stationary value. And that's nice because we don't need to double check that then, do we? When we go through double checking, because it's already given there. And then we need to find a root using the recurrence relationship here. There. So use that recurrence relation, and we need to verify the root. We need these first values. Given x0 is 1.1. So that shouldn't be too difficult. Keep your working quite accurate, because the final answer has to be rounded to 4 decimal places. So the more accurate we can be, maybe to 60p as we work through it perhaps, and then round off to 4 when we get to the value of x3, and then we can verify that this is actually the solution of this equation to 4 decimal places. So number 5, functions of a function, differentiation, product, and function of a function with the power rule. Very easy and nice easy marks there. 7 marks to be gobbled up there really. Inequalities here, and just solving this equation here. Square root, square both sides to get rid of the square root and solve this inequality. Easy question for 5 marks. So the paper's looking great so far. 7, integral. Sine, function of a function here. This is a log of some, oh no it's not, it's something to the minus 2, isn't it? Because this is to the minus 3, so it's a power. Sorry, didn't spot the 3 there for a moment. And then this is a log, isn't it? A log of something, a definite integral there, so work out that. Number 8, got this sketch, and then we just need to translate it and shift it to get this. So translate it over, shift it by 2, and it's good to just check a point here to work out which way it shifts every time to make sure you're happy, and then scale it up by a factor of 3 in the y direction, isn't it? So look out for that one. Another easy question there. Last part of the paper now. F is this, G is this, composite function f composite G, and solve that equation. Nice question here. It's worth doing. Again, no problems there whatsoever, it seems. 10, we've got this function here. Differentiate, write down the range of f. What's interesting here in the calculus is that if the gradient's always positive, then the range of f will simply be, because it's defined on 0 to infinity, the smallest value of f will occur when x tends to 0, is close to 0. So if we put 0 in here, we'll see what it tends to. It will tend to 1 minus 1, won't it? Which is 0. Looks like to me, because that's 0. It'll be 1 minus 2 over 2. 2 over 2 is 1. 1 minus 1 is 0. And the highest value will be if you put in a very large value for x here, say 1000 or 100,000 or a million, you'll see that this becomes really small positive, this fraction, and then it's got a negative attached to it. So it's 1 take away a really small number. So the curve tends to 1 as x gets large. Because it's increasing, f dash is always positive, you've then got the range easily. Then it's very easy to rearrange this for the inverse, and we can then write down the domain and range of the inverse, of course, can't we? So this paper is fairly user-friendly, very nice. I have no qualms whatsoever in doing it sequentially in order, simply because the Simpson's rule question in this paper is not too long-winded. So I just run through it. When you go through this paper, though, of course, when you finish it early, if you do, don't go out and disappear, but make sure you spend the time you have to double check all your questions. The ones especially that need double checking, of course. And then once you've double checked, triple check, so that you squeeze out every last possible mark that you can get for this C3 paper. So all the best then, guys. If you've got a C3 paper in the near future, hope it goes well, and I hope you get some benefit from this worksheet. So hopefully I'll catch you again in another revision sheet. Cheers!